Okay, so this next example is going to be quite long and will take us several videos, uh, but it's very helpful, and it's the sort of the only non-trivial example we're going to do. Um, let's look at the polynomial t to the fourth minus 2 over q. Let's call it f. T to the fourth minus 2 over q. Okay, so we're going to compute the Galois group, and then we're going to go in and look at the Galois correspondence in this situation. Okay, so let's start by computing the Galois group. Let's call the splitting field of f still sigma f over q. Let's call this g. So let's first figure out what sigma f is. We know that f splits over some subfield of C, or C itself, as what? Well, we can set C to be the fourth root of 2. I'm going to, the book uses C, but I don't have a good time writing it, so I'm going to call it beta. So the fourth roots of 2 are what? Well, it's the real fourth root of 2, the negative real fourth root of 2, and then we have those fourth roots of unity, which are the only ones that we're missing are plus or minus I. So t minus I beta and t plus I beta. Okay. So to get access to the roots, all we need is access to the real fourth root of 2 and the imaginary number I. Okay, so that's what our splitting field is. Then when we're going to go and try to reason what the Galois group is, we're going to want to know its size. So we want to know the degree of the extension. The degree of the extension sigma f over q is of course going to be what? Well, we add in a fourth root of 2, which has degree 4. When we add in the real fourth root of 2, we don't have access to I. So then we add in I that has degree 2. So this is going to be an 8, but let's go and do it in steps. So we are going to take q adjoin beta and add in I to get to sigma f. And then, of course, we add in the fourth root of 2 to q as well. So this second step, when we add in an I, is 2, and this first step is a 4. So our extension has degree 8. Okay. So we know that we should be looking for 8 elements of the Galois group. So let's go in and let's try and find them. Let me before we go and look for them, let me give you a geometric picture here. The fourth root of 2 is like here, right? And the negative of the fourth root of 2 is like here. I times the fourth root of 2 is like here. And then negative I times the fourth root of 2 is something like that. So they're vertices of a square that's drawn that way. And what are the symmetries of this object? Well, we have a reflection in the real axis. Okay, so we have a reflection in the real axis. We're going to consider maps sigma from sigma f to sigma f, and also tau, sigma and tau. And where sigma of I is going to be negative I, and sigma of beta is just going to be beta. So in other words, sigma fixes this sort of real part of sigma f and is complex conjugation of the other. So it's this reflection. And then we're going to let tau be the mapping that takes I to I, so it leaves I alone, and then it's going to take beta to I beta. Okay, so what is that going to do? Well, if beta goes to I beta, we're moving that vertex there. I beta is going to go to negative beta. We can see that that will work out. Negative beta will go to negative I beta, and conversely. So we have these two maps here. Sigma is reflection in the real axis, and tau is rotation counterclockwise, of course, by 90 degrees. Now, it suffices to say what an automorphism does to I and beta, but we have to be careful. We can't just say, oh, this is what has to happen. We need to check these are automorphisms. Okay, so how are we going to check their automorphisms? Well, there's a couple ways of doing it. We can verify directly that they define automorphisms. That's kind of not the best way. Let's start with sigma. So let's just claim sigma and tau are automorphisms. So they honestly define elements of G of the Galois group. So sigma, again, is just complex conjugation. So let's notice that t squared plus 1 is irreducible over q adjoin beta. So I and negative I, of course, are conjugates. And I, negative I are conjugates here. Conjugates. And we've seen that if we take conjugate complex numbers and we add them to a field, we adjoin them to a field, then there exists an isomorphism from one to the other, which is the identity on the base field. There exists an isomorphism, which I'm also going to call sigma. Sigma from take q adjoin beta and add in I to take q adjoin beta and add in negative I, such that sigma restricted to q adjoin beta is just the identity. So it fixes beta. And, of course, sigma of I is negative I. Now, both of these fields are the same thing, right? So since these fields are the same, I'm just going to write plus or minus I is just q adjoin beta I. This is our element sigma. Fixes beta and conjugates I. So that's a way of arguing that sigma is an automorphism without directly checking. Because remember, this extension is degree 8. That would be a terrible check. Absolutely terrible. Now, why does tau exist? Well, the reason why tau defines an automorphism is the elements, well, the elements, well, let's say like this. Both beta and I beta have minimal polynomial t to the fourth minus 2 over q. So there exists a q isomorphism from q adjoin beta to q adjoin I beta, which sends, let's call it tau wiggle, which sends beta to I beta. They're conjugate elements. There's an automorphism. There's an isomorphism that takes one to the other. Now, unlike the sigma case, the tau wiggle, it doesn't go from one field to the same field. But we saw that you can always extend this to an automorphism of the splitting field. Extend tau wiggle to an automorphism. Q adjoin beta I to Q adjoin beta I. Right. Any maps within the splitting field will extend to the splitting field. Okay. Now there's a slight problem here. if we were to call this tau, that's fine. When we do this extension, we're adding in I on the left, right? And we're adding in I on the right, or beta, however you want to think about it. When we do that process, we don't know that the automorphism that we're going to get necessarily fixes I. So it could be that tau of I is I, and this is the tau we want. Okay. So that could be the case, but it might not be. It could be tau sends I somewhere else. Now, where could it possibly send I? Well, every automorphism has to preserve the algebraic properties of the number. So I must go to some square root of -1. So what's the other possibility? Well, otherwise tau of I is -I. That's the only other square root of -1. In this case, replace tau with sigma tau. So if tau if the one that we got by the theorem that we proved a while ago sent I to -I, well, sigma is the guy that conjugates. So this will just fix all the betas and send I back. Okay, so this is the one that we would want. All right, so we have sigma and tau are automorphisms, sigma is conjugation, and tau is rotation. And if you recall what you know from group theory, the group generated by reflection in the real axis and rotation by 90 degrees has order 8. And in fact, this is the dihedral group. There's two ways of writing it. You can either write it by the order of the order of the rotation, so rotation by 90 degrees has order 4, or you can write it by the number of elements. I'm going to copy the book and write it as D4 here, and so G is the same as D4, so as a subgroup of S4. And this is it, because this is everything, because this is in fact G, because we can't have anything else. As the splitting field had degree 8. So we should expect 8 elements. We found 8 elements. That is all of them. So this is computing the Galois group. In the subsequent videos, we'll go in and look at the Galois correspondence.